So once again, we have a freezing point depression problem. So right away, might as well write down the equation because we're going to use it. Delta TB equals I times KF times molality. And let's assess what we know. Well, we're looking for, I guess this should be TF. We're looking for this. We don't know it. So what do we know? Well, we know KF. It's given to us right in the problem. So we need to know I and molality to do that. So molality, as we know, is simply moles of solute over kilograms of solvent. So I'm told right off the bat we have 0.2 moles of solute, and there is a 150 grams of water, which is 0.15 kilograms. So the molality is 0.2 divided by 0.15, or 1.33 molal. So I know that as well. So this is really a problem about the Van't Hoff factor and calculating that. So we notice that it says that all of our solid is dissolving, but only half are dissociating. Not all of it is breaking apart. Now, the common thing to jump at is say, oh, half, so I must be 0.5. But what we're forgetting is that a lot of substances don't break apart at all. So for example, if I had 100 particles of NH3, they don't break apart at all, and they make 100 molecules of NH3 dissolved. And so this is a Van't Hoff factor of 1. So we cannot have a Van't Hoff factor below 1. So, forget about that. It's not going to be below 1. We've got to figure something else out. So first off, figure out what does the Van't Hoff factor really mean? What is it figuring out? It's essentially telling you that when you have a certain amount of particles that come in, you multiply it by the Van't Hoff factor, and that tells you how many particles are dissolved, how many are a result of that. So the reason that this is a Van't Hoff factor of 1 is because 100 out of 100, 100 come out, you put 100 in solution, and 100 dissolve and break apart, so that's a Van't Hoff factor of 1. For example, if you had 100 NaCl's, that's going to break apart. It's going to make a total of 200 particles, because it's going to have Na plus and Cl minus. It's going to make a total of 200 things. So the Van't Hoff factor is 200 out of 100, or 2. And I'm picking 100 just because it's an easy number to work with. I really could pick anything. So let's now imagine we have something that dissociates. Half of them are dissociating. And the compound's XY, so any that dissociate break into 2. So if I have 100 of XY, of this 100, 50 of them are going to remain XY. So that's going to produce 50 particles. However, the other 50 XY are going to break apart. I'm going to get 50X out of there, and I'm going to get 50Y, because they're going to break apart. So this is a total of 150 particles, and I only dissolved 100. So the Van't Hoff factor then is effectively 150 over 100. It's 1.5. And so that's the key to this problem, is the fact that the ones that don't dissociate still count. They still affect the freezing point because they are dissolving. And the ones that split apart affect it more because they're splitting apart. So now that I know the Van't Hoff factor, now it's just a matter of plugging it in. So 1.5 times negative 1.86 times 1.33. So 1.5 times these values. And that is going to give me a freezing point depression change of negative 3.7 degrees. So that's my change in freezing point, and since water is usually 0, it also happens to be my final freezing point. Remember, don't get into that trap with the boiling point. All right, and so that's it. So the key to this was the Van't Hoff factor. Be careful. Don't just jump to conclusions about what the value of it is. If it helps, do something like this where you do an analysis and figure out, okay, what is it going to end up being?